cylindrical tank which diameter equals to 1.5 meters and height is 3.5 meters. So, okay, we have two position controller. So that means that we are dealing with on-off control. And our task is we have our set point, and our set point is 3.5 meters. So basically our task is we would like to keep liquid level as close as possible to our set point. But of course we have conditions. So first of all, we are using exact pump, and our pump controls the inflow. So in that case, inflow will be 36 cubic meters per hour. And we have other conditions. We have our outflow, and depending, for example, according to the daytime, so our outflow can be changed from 100 to 500, and units is liters per minute. So again, we have different units. That means that we should use the same. 36 divided by 60 cubic meters per minute will be 0.6 cubic meters per minute. And here 100 liters per minute, this is 0.1. And 500 liters per minute, this is 0.5 cubic meters per minute. So we should use the same units always, otherwise you have trouble. What else? We have another information. We have our condition. So we can turn on, in order that our pump will work for a long time. So we have terms, and condition is that we should turn on and turn off our pump not frequently. So only in every 5 minutes it can be turned on. So basically, if we talk about characteristic of a pump, so the period of that switches will be 5 minutes. The T1 is time when our pump is working, and to T2 there then it's turned off. So this is it. Again,
I have a
yes.
According to this specification, it's only set about 5 minutes on, not period. It could be switched off longer than 5 minutes.
So
I can switch it for 1 second, and then I again have 5 minutes or not.
Maybe I just okay. I will rewrite that sentence. My thought was that period of oscillation, because then we talked about our processes. So here we have the period of oscillations or control signals. So this is the period. This will be 5 minutes. Okay, I will rewrite it in order you can understand it better. So we have such information. So again, I don't remember those equations, so I start from the beginning. I know that the difference of volume during the time will be the difference between input and output. So inflow and outflow. That means that if I have constant outflow here, because inflow can be controlled by the pump. So if I have constant outflow, for example, for some time, 100 liters per minute, so I can describe this dependency as a linear process. So I will have delta V equals to difference between inflow and outflow multiplied by the time during which we observing this process. Because I'm interested in liquid level and our set point is 3.2 meters, so in that case my delta H will be divided by the area of the tank. So let's now consider the case. First of all, as you can see, we have two situations. Then our inflow equals to the maximum which we can give, and then it's turned off. So basically, that means that delta T1 will be equal delta H1 divided by this equation multiplied by the S divided by U in minus U out. So this is situation. Then we have our inflow, and we have another period of time. The second one, where delta H2, and here we have U out. Why I don't have minus here? Because if we consider the situation, basically this is our tank, this is our set point. So because we have here delta H1 and minus delta H2. So here we have minus and here we have a minus, so this is positive. It's obvious. So in our case, so we describe the whole situation, the whole period as delta T1 plus delta T2, and this will be plus delta H2 multiplied by the area and divided by the output. So here delta H1 multiplied by the area and multiplied by the U out plus delta H2 multiplied by the area of the tank multiplied by the Q in for us, basically, it's good to keep those parameters equal. So in that case, I can consider that delta H2 equals to delta H1. So in that case, what we have here? So instead of that, I can just say that we have difference. So basically, the liquid level of our here will change in both directions the same way. So as you can see, those disappear, and we obtain the next situation. It will depend on the inflow, and of course outflow also has its impact on our process. So we have such a situation. So basically we can, in that case, we can calculate what will be the delta H here. So in that case, the inaccuracy in our control, or basically the amplitude of oscillation, will be equal to, so we should divide T by this, so it will be equal T divided by Q in minus Q out multiplied by the Q out, and divided by area of the tank multiplied by the inflow. So let's consider the case then our outflow is minimal. So what error we will have? So phi Q in is 0.6 minus then Q out is minimal multiplied by the minimal. Our area, so and this will be, what I have here, 1.77 square meters. So, according to my calculations, we have here inflow, this is our parameter here. So I will have 0.24 meters. And basically that means that if our outflow is 100 liters per minute, that means that I can keep my liquid level in the range of from 3 meters to 3.4 meters. In case of the maximal outflow. We have such case, 6 minus 5 multiplied by 0.5, and here 0.6. So basically the same situation. Here we have 0.5, and here we have 0.1. So as you can see, the same. But actually, does it mean that if this says that this is our outflow, so does it mean that the inaccuracy of control remains the same all the time? So here we have I think someone more interested in animation. Like that. Right now we have just 24. Does it mean that our characteristic doesn't change? So we have the same error. Unfortunately not. Let's consider the case. So the question is right now, what is the maximum error? So how we can obtain it from the mathematical point of view?
I think the derivative.
Yes, we should use derivative. And basically, because as disturbance we consider our output, so we should take derivative from our delta H by the our outflow. So this is our equation. So let's not that. This is our equation. So I rewrite it a little bit in order to have a better representation. Q in multiplied by the Q out Q in minus T Q out square, and here we have S multiplied by the Q in. So because we would like to find out the derivative by Q out, so basically those parameters can be considered as the constant. So what we have here? We have T multiplied by the Q in divided by S and multiplied by the Q in, and this is it, minus, and here we have again some constant, and we have power, so it will be 2 multiplied by its own value. So what we have here, it's better not to. the external, we should set
This
that
is zero.
function to 0. Basically, that means that our Q in, we have our external, then our inflow.
Equals to double QM.
Yes, that's right. So let's consider that case. Let's consider that case. So, in that case, we will have, for example, Q, because our Q in is such value, so our Q out will be half of that value. So in that case, we have the next situation. 5 multiplied by inflow outflow multiplied by the outflow and divided by area all the time multiplied by the inflow. So in that case, we will have our error double. So basically, what I have here, so representation of our error will be the maximal value here. So like that. And it's not symmetrical because at 3, a little bit here. So the worst case, then the worst case we will have during that. So in that case, we can control the accuracy. So almost 2.8 meters to 3.16.
It's over 4
meters.
It's symmetrical, I guess. Here. It's 0.5 and 0.1.
Yeah. Oh, yeah, we shifted this. Okay, as you can see here, so we have reverse case. So this is it for today, and Projector also said that it's enough. Then next time we will discuss the floating point, or this is some special case of 3-position controller, and I will talk a little bit about a multi-position